In a standard ferromagnetic model, parallel spins create a strong net macroscopic magnetization. This property makes ferromagnets incredibly easy to read in electronic devices, but limits them to relatively slow switching dynamics. Antiferromagnets operate on the inverse principle. Their internal spins align perfectly antiparallel, mathematically canceling out the macroscopic magnetic field. This allows them to switch at highly efficient terahertz frequencies, but renders their data state nearly impossible to detect. For decades, spintronics engineering has been forced into a rigid compromise. You design with the readable spin currents of a ferromagnet or the ultrafast dynamics of an antiferromagnet. You cannot extract both properties from a single material. Recently, researchers identified a third fundamental magnetic phase that circumvents this historical limitation, termed altermagnetism. Combining the absolute zero net magnetization of an antiferromagnet with the strong spin-dependent transport of a ferromagnet requires a total departure from conventional material science models. This diagram shows the formal classification tree of magnetic materials, grouped by their internal symmetries. The first division separates collineal and non-collineal structures. Tracking down the collineal branch, materials split again based on internal lattice compensation. Altermagnets sit exactly here, within the crystal symmetry compensated family. Because their crystal symmetry is perfectly compensated, the opposing atomic spins balance out entirely. The material maintains absolutely zero macroscopic magnetization. The defining physical mechanism driving this phase relies strictly on the geometry of the crystal lattice itself breaking time reversal symmetry, independently of traditional relativistic atomic physics. This specific geometrical origin completely separates altermagnets from both the intricate spin twisting found in non-collinear structures and the uncompensated atomic alignment of standard ferromagnets. In a traditional antiferromagnet, shifting one spin sublattice by a single unit maps every upspin perfectly onto a downspin. This translational symmetry enforces Kramer's degeneracy. Because the spatial sublattices overlap identically, energy states for spin-up and spin-down electrons remain identical across the material. Now examine the physical lattice of ruthenium dioxide, a primary altermagnetic candidate. In this structure, the non-magnetic oxygen atoms occupy a highly anisotropic arrangement surrounding the magnetic ruthenium atoms. Due to the oxygen atom orientation, simple spatial translation fails. Shifting the opposing ruthenium spin sublattices into one another causes the surrounding oxygen geometries to clash. They bypass this clash through only one specific operation, a strict 90-degree spatial rotation. Stripping away translation symmetry and replacing it strictly with rotational symmetry is the foundational physical prerequisite for a material to enter the altermagnetic phase. That specific rotational symmetry in the physical lattice directly dictates how electrons navigate the material, mapping straight into the momentum space band structure. In standard antiferromagnets, this momentum space structure is completely degenerate. Spin-up and spin-down conduction electrons share the exact same energy states at every point. However, the unique 90-degree rotational symmetry of an altermagnet directly forces a phenomenon known as non-relativistic spin splitting, or NRSS. NRSS splits the energy bands apart, organizing them into an alternating D-wave parity pattern. This separates the momentum space into distinct, segregated regions for spin-up and spin-down electrons. This structural splitting proves that a crystal lattice can perfectly cancel its internal magnetic moment in real space while sustaining massive spin polarization for electrical conduction. Historically, separating electron spins in non-centrosymmetric systems without an applied magnetic field required a mechanism called Rashba spin-orbit coupling. Rashba coupling possesses a fatal engineering flaw. It requires the use of high Z, or heavy elements. These atomic structures frequently result in compounds that are thermodynamically and chemically unstable for manufacturing. Altermagnetic spin splitting operates independently of these relativistic atomic constraints. It relies solely on the rotational geometry of the lattice itself. Consequently, engineers can execute massive electron spin splitting using stable, low-Z compounds like metallic oxides and fluorides. By discarding relativistic physics as the driving mechanism, spintronic circuit design is no longer limited by the need to stabilize exotic, fragile materials. Within the material, the segregated d-wave spin structures generate an effect known as Berry curvature. This curvature operates as an intrinsic virtual magnetic field strictly confined within the momentum space. Integrating this localized Berry curvature across the entirety of the Brillouin zone applies a physical force to the conduction electrons, driving them laterally with a transverse velocity. This transverse momentum generates the spontaneous anomalous Hall effect. The material outputs a measurable Hall voltage despite lacking any net internal magnetization or external magnetic field. This chart maps transport properties to mathematical point groups, from pure antiferromagnetism on the left to ferromagnetism on the right. The dashed ellipse reveals type 1 altermagnets actually classify within the ferromagnetic group, explaining why they exhibit the linear anomalous Hall effect. The point group classifications and Berry curvature calculations verify that the theoretical geometry of altermagnets reliably generates observable physical spin currents. Density functional theory currently identifies over 200 distinct altermagnetic candidate materials. However, achieving successful experimental verification of these theoretical geometries in laboratory settings remains extremely rare. A definitive laboratory confirmation was achieved by analyzing epitaxial thin films of chromium antimonide using angle-resolved photoemission spectroscopy, or ARPES. The bright intensity map on the left represents actual energy states measured from the sample, showing a massive 0.6 electron-volt spin splitting. Compared to the three-dimensional model on the right, the empirical data aligns perfectly with the predicted D-wave parity. This reading proves that non-relativistic spin splitting extends beyond theoretical mathematics. It exists within physical atomic substrates, and importantly, it persists at room temperature. Despite confirmed cases like chromium antimonide, ruthenium dioxide, the most intensely studied altermagnetic candidate, is currently the subject of highly contradictory literature. Early theoretical modeling predicted significant spin transport properties, yet recent high-precision neutron diffraction experiments suggest that the material's observed magnetic signals may be entirely false, arising simply from scattering defects in the physical samples. Theorists utilizing density functional theory argue against this conclusion. They calculate that true altermagnetism in ruthenium dioxide is incredibly fragile, demanding flawless chemical stoichiometry to function. To trigger and stabilize the non-relativistic splitting in this specific crystal, researchers must engineer highly specific physical conditions, such as intentional hole doping or the introduction of precise atomic ruthenium vacancies. Resolving these limits provides the blueprint for spintronic components, offering ultra-fast terahertz switching speeds, paired seamlessly with total immunity to external magnetic fields. The core physics of altermagnetism are mathematically and empirically sound. Implementing this phase to build low-power, high-speed information infrastructure now depends entirely on mastering atom-perfect material synthesis.